So let's go ahead and look at an example where we have another indeterminate form that's not a L'Hopital's. And basically what we do with these other indeterminate forms, is we try and get them to a point where I can use L'Hopital's. Now remember, to use L'Hopital's you need a numerator and a denominator, so a lot of times these take a little bit of a rewrite. So let's go ahead and look at an example. With this example, let's take the limit as x approaches infinity of 1 plus 1 over x to the x. Now if we plug directly in, we get 1 plus 1. Here this x is approaching infinity. This entire fraction is going towards 0, so I get 1 plus 0, which of course is 1, and of course my power here is to the infinity. This is indeterminate. This does not mean indeterminate L'Hopital's, it's just an indeterminate form. Now remember, when we have an indeterminate form, it's do more work. But because I have a variable to a variable here, the more work that I should do is to use the natural log function. So what we're going to do is come up with a solution. We're going to say the solution to this limit is y. Set it equal to y, and the reason we want it set equal to something is so we can equate two sides, so we can balance an equation. So I have to have that equality in there. And then we'll take the natural log of both sides. So I have the natural log of y equals the natural log of the limit as x approaches infinity of my function. Now we're going to be standing on the shoulders of some giants here that proved a lot of things that make this process a little bit easier, and we're actually going to say the log of the limits is the limit of the logs. So this is already a previously proven theorem that we can use. So I have 1 plus 1 over x to the x. Now using our laws of logs, I can pull that x that's in the exponent out front. So I have x ln 1 plus 1 over x. Now what I'd like to do is to go ahead and take this limit again. Now the left hand side I'm not doing anything with right now, I'm just dragging it along. On the right hand side, the limit as x approaches infinity of x is just equal to infinity. The limit as x approaches infinity of 1 plus 1 over x, this 1 over x is going to go towards 0. 0 plus 1 is 1, and the natural log of 1 is 0. This is indeterminate as well. So far I've gotten 1 to the infinity, which is indeterminate. I've gotten infinity times 0, which is indeterminate in the same problem. So it doesn't seem like I'm making any progress. But the key here now is to rewrite. So the left hand side I'm dragging along. Now the rewrite that is common to make is to remember that I need a numerator and a denominator. Right now I just really have one large numerator. Now here what I want to do is take this x and flip it into the denominator. So this value of x right here in the numerator becomes 1 over x in the denominator. So now I have a numerator and denominator, and it's my hope that when we take our limit again, that I will actually be able to use L'Hopital's to make this process a little bit easier. So let's go ahead and take that limit. First of all, in the denominator, 1 over x as x approaches infinity goes towards 0. This fraction 1 over x goes towards 0, and the natural log of 1 is 0. So now I have that lovely indeterminate L'Hopital's, and I can apply L'Hopital's rule. So for L'Hopital's rule, I have the natural log of y equals the limit as x approaches infinity. L'Hopital's rule says I take the derivative of the numerator over the derivative of the denominator. It's not the quotient rule. So the derivative up here of the natural log of u is 1 over u times the derivative of u. And the derivative of 1 is 0. The derivative of 1 over x is negative 1 over x squared. And in the denominator, the derivative of 1 over x is negative 1 over x squared. So from here I have the natural log of y equals the limit as x approaches infinity, and I get some canceling to occur here. Both of these cancel. And I'm left with 1 over 1 plus 1 over x. Now from here, as I take this limit, this term goes towards 0, and I'm left with 1 over 1 plus 0, which of course is 1. But that is not my solution. Remember, we have the natural log of y is equal to 1. So let's go ahead and look at our final steps for our solution. We have the natural log of y is equal to 1. Well, if you remember, the natural log of e is equal to 1. Therefore, y equals e is my solution. But if you don't remember that, you could rewrite this as log base e of y equals 1. And then remembering, of course, this can be rewritten as e to the first equals y. E to the first equals y, therefore y equals e this way as well. So what I have here is that 1 to the infinity as my limit solution in determinate form actually equals e eventually. Let's go ahead and look at another rational expression that I want to take the limit of. Okay, the next one we're going to look at is the limit as x approaches 0 of the cotangent of x minus 1 over x. So of course, first thing we do is plug directly in. The cotangent of x, that's cosine over sine. So the cotangent is equal to the cosine of 0. The cosine of 0 is 1. The sine of 0 is 0 minus 1 over 0. Now this is an indeterminate form, but it is not an indeterminate L'Hopital's form. So I have to figure out a strategy here. And the strategy that I'm going to do here is some more work and rewrite it. So let's go ahead and look at a rewrite. I think for our rewrite, and please note here you never drop your limit notation, is going ahead and finding a common denominator and rewriting our cotangent. So again, cotangent is cosine of x over sine of x minus 1 over x. My common denominator is going to be x sine of x. So this is going to be x cosine of x minus sine of x. Now this actually looks quite a bit worse, but maybe it might work. So let's go ahead and take our limit. And I drop my limit notation just like I just asked you not to, so that you'll see why it's important not to drop that now. Limit as x approaches 0. So let's go ahead and look at our graph here, or plugging into our value here. If I plug 0 into the denominator, I get 0 times the sine of 0, which is 0 times 0 is 0. Now up in the numerator, I have 0 times the cosine of 0. So 0 when I plug in for x, the cosine of 0 is 1, minus the sine of 0. And remember, the sine of 0 is equal to 0. So again, I get 0 over 0, which is indeterminate L'Hopital's. Well, the question is, what to do here? Can I figure out anything? Is there a rewrite? Well, since I can use L'Hopital's, it might be a good idea to actually go through and take some derivatives. Now, these derivatives do not look fun to take. I see a product rule here. So I have the first times the derivative of the second, plus the second times the derivative of the first. Okay, that's for this first product, minus the derivative of the sine of x is cosine of x. Now in my denominator, I'll have first times the derivative of the second, plus the second times the derivative of x, which is 1. Now our hope is something might cancel. I don't really see that happening. Well, I guess I do. Up here in the numerator, I have a cosine x minus cosine x goes towards 0. So this does simplify a little bit as the limit as x approaches 0 of x, I'll call it negative x sine of x, over x cosine of x. And of course the x's will cancel. That's nice. And I'm left with the limit as x approaches 0 of negative sine of x over cosine of x. Now if you wanted to, you could rewrite this as tangent, but in its current form it kind of makes it easy to plug into. So let's go ahead and plug in. Plugging in our negative, or dragging along our negative, the sine of 0 is 0, cosine of 0 is 1, and I get 0 for this limit. Well, that was a lot of work. Let's go ahead and see if Maple graph might agree with what we got for our limiting value. So we can see here from our Maple graph that we're interested in looking at the limit as x approaches 0. So as we approach 0 from the right, my y value goes towards 0. As I approach 0 from the left, my y value approaches 0. So it does seem that this graph supports the fact that the overall limiting value is 0. So that looks pretty reasonable. In the last part of the lecture, we're going to be looking at determining which function goes faster in a rational expression. In the discussion about determining which function grows faster, it's a good idea to read through pages 387 and 388 in your textbook. It gives a really nice little comp sci example that you might be interested in. First of all, we're given a theorem in this section that basically says if I have a variable like x to a power, this is always going to be, I'm sorry, that's the wrong notation there, much less than e to the x. So this is saying a polynomial function is going to be growing much slower than an exponential function. And this is true for every exponent n. And wow, that's a pretty strong statement. So an exponential function grows faster than a polynomial function is kind of what we're getting at there. I'd like to look at one last example. The limit as x approaches infinity of e to the 2x plus 1 all over x to the 10th. Now x to the 10th is huge. If we take 2 to the 10th, I get like 1024. So it's growing really, really fast. In the numerator we have an exponential function. So let's go ahead and compare and see what's happening here. First of all, if I take the limit as x approaches infinity in my numerator, I approach infinity. My denominator approaches infinity. So, of course, this is indeterminate L'Hopital's. Well, indeterminate L'Hopital's means I need to take some derivatives. So let's go ahead and start with that. Limit as x approaches infinity. The derivative of e to the u is e to the u times the derivative of u. The derivative of 2x plus 1 is 2. Now the derivative in the denominator would be the derivative of x to the 10th. The derivative of x to the 10th is 10x to the 9th. Take the limit, and again, I get infinity over an infinity, which is indeterminate L'Hopital's. So I do everything again. We're going to start to see a pattern here, and we should be able to estimate exactly what's happening here. I drag the 2 along. The derivative of e to the u prime, and I'm just going to write this as 2 times 2 for now. The derivative of my denominator will be 10 times 9 times x to the 8th, which is going to equal infinity over infinity, indeterminate L'Hopital's, and we're going to run through the process again. So let's look at the limit as x approaches infinity of 2 times 2 times 2 e to the 2x plus 1. That's another e to the u prime. And in my denominator I'll have 10 times 9 times 8 x to the 7th. And I'm going to get infinity over infinity again, another indeterminate L'Hopital's, and I'm going to repeat this process. Now this is going to keep repeating until right before, the derivative before, the denominator goes to 0. So what this is going to do is it's going to follow through with this pattern, and it's going to look like the limit as x approaches infinity of 2 to the 10th, e to the 2x plus 1, all over 10 factorial. And 10 factorial is 10 times 9, 8 times 7 times 6 times 4 times 3 times 2 times 1. And because of this theorem up here that says an exponential function grows faster than a polynomial, so I know this exponential function is growing very, very rapidly. This is a factorial. It grows rapidly as well, but it does not trump the exponential. So this is going toward infinity, and I'd have to say therefore the limit does not exist. Okay, so there's another example where I used L'Hopital's multiple times. This one got a pattern developed, so it was a little bit easier to work with. If this had been e to the 2x plus 1 over x to the 100th, we certainly would not have wanted to go through 100 iterations of L'Hopital's to come up with this. So it is nice to look at these patterns.